Thank you very much. So first of all, thanks to the organizers for including me in this Sergio Fest. It's really a pleasure. I met Sergio for the first time. I don't know if you remember, but I remember because I was a student, in fact, at ENS, and you were spending some sabbatical year or half year in Paris.
This Pascal stuff.
96 or something like that. Exactly, yeah, Pascal. And you came to ENS, you gave a mini course on Fourier restriction, which I attended. And then you also were co-organizing with Chaim Brezis this weekly seminar, which I also attended every week. But then later we had time to get better acquainted. It's always been a pleasure to run into you on either side of the Atlantic. So, like me, Sergio has a bit of a delocalized phase, oscillations.
It's mostly here that we met.
Yeah, but Princeton also, many times, right? Okay, anyway, so it's a happy occasion. Many years have passed. So today I want to talk about mean field limits. So the question is to derive effective equations for systems of points, which you can think of as particles, which interact and move. So this is the setup. We have n points in our space Rd, and there's an ODE system for their dynamics. Each point moves with velocity equal to some average force, which depends on the location of the point and on the location of all the other points in the system. Okay, and so it's mean field because it's, as you see, it's an average over all the other particles, including the far one. And what we want to think about is, in particular, the case where the interaction can be quite singular when two particles get close to each other. So if x and y are close, we want to think that this k can blow up like 1 over distance to the power s plus 1. So s is going to be a parameter that you encounter for the rest of the talk. So why do I write here s plus 1? Because I want to think that, for instance, in the case that this derives from a gradient, then it would be the gradient of 1 over power s. Okay, so s would be that power here. But I'm not going to always assume it derives from a gradient. This is just two fixed ideas, right? You can consider gradient flows, but you could also consider maybe opposite gradient flows. So in general, if you don't prescribe any structure, K could be kind of attractive or repulsive, or neither attractive nor repulsive. And the other ingredient you could add, I'm not going to do it formally, just mention you can do it. You could add some diffusion term here, like in the form of independent Brownian motions for all particles. That's the most standard thing.
Can you add also two derivatives on the x?
I would like not to have two derivatives on the x. That's a very good question. So first of all, okay, in principle, you could tell me, you know that any second order system you can put in a first order form, but then it's not going to fall into my thing. So yeah, second order is much harder. And there are some cases in which it's okay, but for simplicity, most of our results that are the most new only work for first order, because second is harder. But yeah. Okay. So the question is, you want to derive the effective dynamics, so you want to take the empirical measure of the particles at their positions xit, and take the limit in time and find that it converges to some distribution, some measure, probability measure mu t. An alternative way of thinking of it is you can set up the joint law of the initial particles positions, called that Fn. It's a function of x1, xn. And there is an initial one, and you ask what is the subsequent joint law. You can throw the initial values, initial positions at random if you want, or you can even think of it deterministically. And there is this important notion of propagation of chaos, which is that if the initial distribution is in a tensorized state, then at later times, you can also approximate it by a tensorized state. So that means if your initial laws are IID, then it remains so, and it's a form of independence of the particle's positions. So if you have that, you say you have propagation of chaos, and to measure this, usually you look at k-point marginals, for instance, f and k, so you integrate over all particles except the k, a fixed number of them, and you try to take the limit. Okay, so it turns out that these 2 points of views are essentially equivalent to each other, and are both propagation of chaos, mean field limit. And in terms of the PDE, so what you expect, or what you formally derive, is that this mu-t limit should solve a PDE, which is a continuity equation, right? So dt mu plus divergence of a velocity field, which is the convolution of k with mu times mu equals 0. So this velocity field, you define it like this, or you compute it like that, right? So convolution here means I just integrate with respect to the second variable. Okay, so the question is to prove this rigorously, even though it's easy to derive formally. And it's particularly delicate when k is singular. Okay, motivations, in case it's not clear that this is useful, I don't know. Of course, you can think of this as ways to derive effective or macroscopic theories from microscopic dynamics. You encounter such systems in fluids, for instance, the point vortex system, in superconductors, superfluids, in biology, social sciences, where these points represent agents. You can also use these dynamics, these gradient flow dynamics, to approximate in long time minima of interaction energies. So that's actually quite used in optimizing parameters in neural networks these days, or in statistics with maximum mean discrepancies. And if you add noise, you have all this family of problems of the type of stochastic gradient descent, sampling algorithms, etc. And of course, it has also physical meaning as Langevin dynamics. Okay, so there's many problems in some sense that can be recast in such a form. And the approaches to proving convergence that are classical usually require quite some regularity for the force kernel K. So I'm going to list a few. So originally the most classical one is a sort of trajectorial method initiated by McKean. The idea is that you compare the trajectories of the particles to basically the trajectories of fictitious particles that would follow the characteristics for the limiting equation. Okay, so you have a limiting equation, you take particles, you let them follow the characteristics, you start them at the same initial positions, and you try to see how much the distance from the true particles to the fictitious one is evolving in time, and you prove a Grandval relation that can be nicely closed as long as k is, say, Lipschitz. Okay? So if you make an error on the position, you want that the error in the force is not very large. So that's quite natural. More general idea is find a good metric. So a distance that's going to quantify, how close your empirical measure is to the expected distribution. So one that has been quite popular is the class of Wasserstein distances. Okay, and so what you want to do again is to prove some kind of, I call that a Grandval relation. So the time derivative of the distance between, say, two solutions of the mean field evolution, you want to show it's controlled by a constant times the same distance. And if you can do that at the level of the mean field evolution, of course it buys you uniqueness and stability, etc. But then you can try to apply it to the empirical measure itself and the limiting distribution. Even though the empirical measure doesn't solve exactly the same PDE, but you can think of it as an approximate solution, and you can try to compute this time derivative and see if you can close prove a relation like that. Okay, so usually that works also with some good regularity for K. Okay, and then there is this singular case, which is also quite manageable, which is the 2D Coulomb case, because the 2D Coulomb is logarithmic interaction. And logarithm is singular, but barely, right? So you can still basically go through passing to the limit in the equation, more or less. And that has been done a lot in conjunction with the point vortex system or particle method, if you want, in fluid. Okay. With noise, very successful method is the relative entropy method, which was in particular revitalized by a paper by Jabin and Wang in 2016. You look at the relative entropy, and this time you phrase it in terms of the laws of the particle distributions Fn that I talked about before, and relative to rho n, or this could be mu tensor n times. So this is the standard relative entropy. Of course, it's non-negative, and it's a bit like a distance, so it quantifies convergence. If you can close, again, a Grandval relation for this. And they managed to close it for this class of force fields, so that's now starting to be a bit less regular. Still doesn't allow for the inverse power singularities that I want to be interested in. And this also requires noise. Then there was recently a very nice paper by two grad students at Courant at the time, Riesz and Rowan. I introduced a different metric, which is in fact not so, also quite used in statistics and stuff like that, which is the chi-squared divergence metric. So you measure here the k-point marginal distances in a sort of weighted L2 sense. Well, that's the definition. And what's nice with their work is that they're able to expand to all order and to get a convergence rate which is sharp, which is in 1 over n for these quantities, and do a sort of cluster expansion, getting the limits in a BBGKY hierarchy associated to the equations. And they can give you basically the corrections. But it works for bounded K. Okay, so now I talked about, the title has two methods, so two methods that are designed to be able to handle these singular interactions when two particles get close. So the first one has been now some years old, is the modulated energy method approach. And it is going to specialize to a particular situation where basically our system derives from an energy. So there is an underlying energy. And that's going to be a very strong help, if you want. Okay, so in this context, I'm going to restrict to the setting where K is symmetric and derives from an energy in the following form. So it's a gradient of a, so not only it's symmetric, but it depends only on the vector x minus y. It's the gradient of a certain g of x minus y. And here you can put a matrix M, which has to be a negative matrix. Okay, so if you want to be simple, just take minus identity, then you get the gradient flow. The possibility of having the matrix allows you to do antisymmetric operations, for instance, if you want. So that includes point vortex system and things like that. Okay?
Symmetric, it's anti-symmetric.
No, K itself is symmetric, right? Ah, no, you're right, it's antisymmetric. Very good. Good point. Antisymmetry. Thank you. It's the G that's symmetric, but not the, yes, it's symmetric up to sign. Very, very good point. Okay, so the model case that we want to keep in mind is this exact inverse powers of the distance, which I call Riesz interactions. Okay, so 1 over x to the s, it's convenient to put an s in the denominator here. And you want to ask that s is strictly less than the underlying dimension of the space, because beyond that, the singularity is so strong that first of all, the kernel is no longer integrable near the origin. G is no longer integrable. And the effective dynamics is no longer a mean field because this become very short-range interactions in some sense. And so the far particles don't count very much. So the limiting dynamics is not the one that I wrote. Okay, so this is why we always restrict to S less than D. And when S is 0, you should think of it as the log. So this degenerates into minus log. And in particular case is in all dimensions, S equals D minus 2 is the Newtonian or Coulomb potential. Okay, so it works also in dimension 2, where S is 0, interaction is minus log. Okay, so that's why it's physically important to be able to treat these types of interactions. And so the method combines the idea of finding a good metric with the idea of there is an underlying energy. So what we do is we build a metric that's based on the energy and that's based on the interaction. Okay, so it's a Coulomb/Riesz based metric. It's based on G. And the simplest form of it is this. So if you have two probability densities mu and nu, you define the norm squared to be this double integral. So this double integral is a sort of interaction, right? A total interaction of your system with a positive density mu and negative density minus nu. So you count all the pair interactions of your infinitesimal, if you want, infinitesimal pair interactions, and you add them up. Okay, in the particular case where G is Riesz, in fact, you can very quickly see that this is just some negative Sobolev norm. If you go to Fourier, it becomes a integral of G hat squared. Sorry, G hat. Right, so now this is some sort of inverse power, and you have just a Sobolev norm. So okay, this is going to be a good metric. The problem is that this metric, even though it's related to the energy, this metric does not accept empirical measures. It does not accept Diracs, because at a Dirac, you would have G of 0 for the self-interaction, and that would be plus infinity, because the assumption is that G is infinity as 0. So to deal with that, we define now the modulated energy in the following way. We put the empirical measure, we subtract off our reference measure mu, and the difference is that we remove the diagonal. So in other words, we remove the self-interactions, just take them out. So now this becomes a finite quantity. And the problem is you may have lost the sort of metric nature of it. So that's going to make things difficult, but the idea is that in the end it does behave almost as a metric, and it's a good quantity, it's coercive. You can use it to metrize convergence. But the difficulty, technically, if you want, lies in this renormalization of it, if you want. Okay, so the idea is we're going to put here for xn, so capital Xn is a proxy for the whole configuration, little x1, little xn. We're going to take the evolving configuration for capital Xn, and for mu, we're going to take the expected solution, so the solution to our mean field equation. All right? So this was a method that was introduced in 2 papers, one on Gibbs-Borlando and one by Mitya-Dirinx on this discrete problem. And so now you want to differentiate this thing in time. So now that you have a quantity, which is supposed to be like a metric, you differentiate in time, and you want to control it by itself, the derivative, Fn. Okay, so when you compute, you use the fact that xnt solves the ODE system, you use the fact that mu-t solves a certain PDE, and you find yourself with the right-hand side, which is exactly this quantity. And it involves a certain vector field Vt. And what is Vt? Vt is just, in fact, the velocity field associated to your limiting equation. Right, so if I remind you, that's the limiting equation. And here in my particular case, this is m grad g u. And so that's v. That's the velocity field. Okay? And so in order to bound this by Fn, in fact, what we realize is that we have to prove a functional inequality. This is not going to depend on the specifics of the particular dynamics. It's going to depend just on the fact that this functional inequality always holds true for any configuration of points that are distinct points, for a vector field that's regular enough, and a density mu that has some regularity. So we're going to assume it, for simplicity here, L infinity to have a bounded density. Okay, so this inequality is always true. So you see here, G has a singularity, which is an inverse power. Okay, so gradient G has one more derivative, one more power in the denominator. And if you assume that V is Lipschitz, for instance, you can recover here another x minus y. So you can sort of cancel. In terms of homogeneity, this thing is going to be like 1 over x minus y to the s plus 1. And then Lipschitz norm of V. And you regain another x minus y. So this does have the same homogeneity as G, which is why this relation is sort of credible. However, this does not make a proof, because you would have to take absolute values and get rid of cancellation. There's a strong cancellation happening in the inequality. Okay, so the result is this, and it was proven in several installments with, you know, sharper and sharper estimates. There's a constant that depends on the gradient V. I'm going to be more specific on the next slide, which bounds this constant times the modulated energy plus a term which is small. So here there is an infinity norm, and here minus 1 plus s over d is always a negative power, because s is less than d. Okay, so s over d minus 1, that's negative. So this is a small error which is not harmful, and we call this a commutator estimate. Why? Because if you break up the minus sign here into two pieces, you can rewrite your double integral with some convolutions, and you can observe that what you're doing is this. You're doing v dotted gradient g convolved with f, so f is this whole difference between empirical measure and mu, and then here minus g convolved with the divergence of vf. Okay, so you're doing two operations, three operations, you know, in different orders, and you can really think of it as a commutator. So why we call it a commutator estimate. However, you can't really apply standard commutator estimates for several reasons, but one of them being that you have to worry about this thing with this removal of the diagonal, so you're not really in a... You have to handle this renormalization step, in fact. Okay, and the error rate that we obtain here, so it took some time to get to this rate, but now we got there, and this is sharp. For certain reasons, you cannot hope for better than that. Okay, so what...
Is it where you have to use the sign K?
You use what?
The sign of K. Because for you, K equal m gradient G, and it's the sign of m.
So the sign of m came in the previous inequality, sorry. When you compute the time derivative, here, it's to have this inequality. Okay, so if it's dissipative, you get a negative term here that you throw away. If it's conservative, you get an equality term. But if you don't have the sign, then you would get an extra term here. So it's you take advantage of the energy conservation / loss at that point. Okay, so what is this dependence in V in our estimate? So we have actually two different papers that give two different estimates. the latest, estimates. One with Matt Rosenzweig is restricted to the situation where S is bigger than D minus 2, which is, so it's super Coulomb, right? So it includes Coulomb and more singular than Coulomb up to D. And then we can just take this constant to be the norm, L infinity norm of the gradient. So if you want the Lipschitz norm. That's quite satisfactory. We can also estimate in terms of LP norms of mu. If you don't want the L infinity norm, that's okay. And this proof runs by electric formulation plus stress energy tensor structure inside this sort of commutator terms, which if I had time at the end, I would show you, but I don't think I will. There's also higher order versions of the estimates that are proved in that paper, and also the estimate can be localized, which is very useful for other things. What I mean by localized is that if V is supported in a small region, you want this thing to be able to bound by something that's also supported in that small region. Okay, so then we have a different proof in a paper with Elias Hess-Charles and Matt Rosenzweig. Works for all these S, even for S negative up to minus 2. And then so again, it gets the sharp error rate, but the constant, you have to have the Lipschitz norm, but you have to add another thing that contains more derivatives of V. And then we prove in a more recent paper that this is also kind of sharp. You really do need these extra derivatives when S is less than D minus 2. So this proof works by a different method, using a sort of wavelet decomposition of G, commutator estimates, but it has the disadvantage you can't localize it, you don't have higher order versions, etc. Okay, so just for the pleasure of analysis, you want to investigate, how much can you push on these things, and in particular, one of the reasons is because you have to put for V here. Right, remember this V that you have to control here is the velocity field of your solution. So it would be better if you can control with V in the norm that corresponds to the regularity of your solution. Okay, so that's this, right, for this guy. Okay, but so what is the natural regularity space for mu t? For instance, it's a scale invariant space for the PDE. So you would like to be able to control with just Vt in that corresponding space. And here you cannot, so that's why we have to assume more regularity of the limiting solution if you want. So that's why we sort of investigated this, and we found that the estimate that we have cannot be relaxed. The regularity cannot be relaxed. For instance, if you assume only gradient V in BMO, which is slightly weaker than L infinity, it's false. You can find counterexamples. We also find, so it's a more recent paper, the same two, that if G is less singular, then you need more regularity of V. There's a sort of trade-off. And you can, however, do something if you have less regularity, which we can obtain what we call a defected commutator estimate. So an estimate where you're going to have the same control as before with the same constant, with a less regularity of V assumed, but a sort of bad constant in front, with an added term which can be very large, but you can put a very small constant in front. Okay, and so under assumptions of good initial data that will suffice to run the mean field limit proof through, assuming less regularity on V, in particular, you can be in that scaling critical space, which is written here. Okay, so the thing I wanted to maybe convince you of is that this is the key, right? Once you have this commutator estimate, everything else is just direct computations. You plug that into here. You convince yourself that Fn is a good metric, and then you're done. Okay, so now I can state the theorem. Theorem is here. So if you have a regular enough solution so that you can apply your commutator estimate, you're going to bound the modulated energy at time t by the initial one plus this extra additive term, which is small, times an exponential in time. That's due to the Grandval relation. And so in particular, if you have initial data which satisfies this limit equals to 0, which is just convergence of the initial energies really, then you will have convergence of the empirical measures. And okay, the problem is solved modulo this sort of PDE question of how regular can you get your solutions to the limiting equation. Okay, so I described this for G being exactly Riesz, so exactly some inverse powers. But in fact, now our commutator estimates work for a certain class of, you can call them Riesz-like interactions. So really what you need is the repulsiveness, the fact that G is a good kernel from which you can make a metric and has this repulsive nature. So you can include, for instance, certain Leonard-Job types potentials. It doesn't have to be exactly inverse power. These estimates have been used in other contexts. You can use them for quantum mean field limits, for quasi-neutral limits. Going back to your question, you can use them for second-order equations, second-order evolutions, but so far only in the monokinetic situation, which is an assumption that at each position in space there is a unique velocity. So you don't have a distribution of velocities, you have a Dirac at a given velocity. So under that assumption, you can converge to the corresponding Vlasov equation.
And the initial data, they are restricted to the random IID?
So the locations of the particles can be IID, but at each position, there's a unique velocity. It's sort of...
The theorem. You assume nothing about the initial data?
Yeah, I assume just these two things. Convergence to some initial distribution and convergence in energy. Okay, so you approximate well. You have a limiting initial distribution and you're approximating it quite well. Okay, but there's no probabilistic discussion here. Okay, so with noise, precisely, if you want to make it probabilistic, there is a variant of the method which is the modulated free energy method, which incorporates noise, that was developed by Riesz, Jabin, Wang. And there's various works that aim to obtain long-time convergence, so things that are not limited to a fixed interval of time. Different approaches have been used. One is to use the decay of the solutions to be able to get a Grandval relation with something that's integrable in time. Another approach is to use functional inequalities. And a remark is that you can also treat some attractive interactions this way. In particular, in fact, you can treat the attractive log interaction, which was one of the motivations for these things, related to a discrete approximation of Patlack, Keller, Segel, in particular, was a motivation for these studies. But okay, I want to switch to the second method. Multiscale mollification. So now we go back to the original setting. Velocity is equal to average force. And I don't want to assume now that this thing derives from an energy. Okay, so that's not going to be assumed. On the other hand, I still want to assume that the singularity is, like 1 over x minus y. So here s plus 1, because as I told you, it would be corresponding in the case where it derives from an energy. Okay, so we have a list of assumptions. I'm not going to list them because it's long, but the idea is that you have it also for the derivatives of k, and you assume this almost anti-symmetry. No. Almost a function of x minus y, at least in the most singular parts, right? So you can add non-symmetric parts and things like that. As long as they are less singular, it's okay. So this is, by the way, ongoing work with Hung and Nguyen. Okay, and so we're going to assume S less than D minus 2. So remember, S equal D minus 2 is Coulomb. That's a good goal to have. and below it's sub-Coulomb. But now things can be attractive or whatever. There's no energy control. We're always going to assume that the limiting solution is as regular as we want. Okay, so here is another idea of a metric. So still looking for metrics. We use a standard heat kernel with a length scale eta. Okay, so here eta is for length scale. So think of it as length scales that can range from n minus 1 over d to 1. So you have your assembly of points. There's n of them. So of course n minus 1 over d is the sort of micro scale, right? If you have points in a fixed domain. So it's the super microscopic length scales, maybe. And so what you do to measure now is you take your empirical measure, you mollify it by convolving by this phi eta, and you look at the difference with the expected density mu. Okay, and you take that in L infinity, so it's really the soup. So the only thing is here we add a weight. So this is the Japanese bracket, gamma is some large power. So the goal of that is just to basically localize things in space, okay? So that things decay fast at infinity. This is just technical. But so this is a distance, right? So for every length scale eta, you mollify at this scale. So you're gonna create blobs, right, around all these points, and they're gonna be superimposed, and you measure in L infinity the distance to mu. We will also use a weaker metric, so W like weak. It's the same quantity, but now you measure it in a weak space. You see the dual of W11. Okay, so first attempt, you say, okay, let's differentiate in time and let's see if we can, maybe get a Grandval relation. And of course, you immediately see this is completely hopeless. Because the time derivative of the thing is not controlled by the thing itself, but is going to need a control at the smaller scales than eta. So what you can do is you can use the semi-group property of the heat kernel, which is quite nice because it allows you to relate things at one scale to another. And you can find a sort of multiscale control. Okay, so here eta 0 is the smallest scale, n minus 1 over d, so that's really the interparticle length scale. And you make dyadic decomposition, so eta is some dyadic power, 2 to the n times eta naught. And what you're going to do is basically you're going to decompose, for each particle, look at all the interactions with the other particles that live at a certain dyadic scale. And then you find a relation like that. You can bound the time derivative of this thing in terms of something small plus a sum of the same things but at smaller scales. Right? So 2 to the k eta naught, when k is less than n minus 1, it's less than this guy. So it's all the smaller scales multiplied by something like that. So this is not really a problem. So you decompose until you arrive at the smaller scale. At some point you have to work. So you also have the contribution of the smallest scales, which are microscopic and below. Okay, so here it's important, this factor here is important. And this is still not going to work on its own. To control the smaller scales, we're going to have to couple basically the evolution of these quantities with the evolution of another quantity which is going to precisely control what's happening for small scale interactions. So you see here, this h, you have a cutoff, so k is a cutoff for pairs of points that are only at, it sees pairs of points that are only at distances less than eta, and it counts the maximal thing you can have, so the inverse distance to the d minus theta over 2. And what is theta here? Theta is d minus s minus 2. So it's basically the margin you have to be in Coulomb. Because you have a theta margin to be in Coulomb, you take theta over 2. And you see here that there's going to be different situations according to the situation where you Coulomb or sub-Coulomb. Because for sub-Coulomb you have some margin, and for Coulomb you have no margin. Anyway, so you can study the time evolution of that guy and be able to bound its value at time t in terms of the initial value and the m norm. And so you're going to be able to sort of couple the two. So this leads to introducing a multiscale metric now, where you're going to sum these metrics over dyadic scales. So it's going to count things at all scales with some factor here that makes it so that small scales get discounted. Okay, so the smaller the scale, the less you count it. And the idea is to try to look now at the time evolution of that thing and see if we can close some kind of Grunwald relation for that. All right. So if you can bound this thing, so the remark is that this thing, you just need to prove that it's bounded. Because if it's bounded, then it controls things at smaller scales. You can control in terms of an inverse power of 2 now times the thing. So if this guy is bounded, since this is going to be very small, you're going to have that the small scales things are small. So okay, so this thing bounded implies convergence. Of course, you have to accept the idea that if you can bound, if you ensure that one of these m of etas go to 0, you have convergence of the empirical measures. Right? So if for one eta m x and mu eta goes to 0, you already are done in terms of getting convergence. Okay, you're going to get it corresponding to that scale, but for weak convergence, this is plenty. Okay, so then later we'll be able to go back, use the equation, and also estimate weak norms, but I'm not going to give details. So we're almost done. Don't worry. So the idea is now you have this notion of doing it at multiscale. So what you want to do is you want to multiply these relations that I had obtained before by a factor which is 2 to the sigma n, and then sum all the relations. So we go back to that thing, equation 1. We have this thing at a given scale in terms of the lower, smaller scales. And we want to add both sides up, basically, sum on both sides. And the reason why things work is because we have this factor here that's going to make one of the sums converge. Because when you sum these things, you have a double sum. And so things converge, luckily. And eventually, you're able to prove something like that on this multiscale quantity. Okay, so it's not quite what you would have dreamed of, dtm less than cm, because now you have a squared here. Okay, so what happens when you have an ODE of that sort is it can blow up in finite time, right? dtu less than u squared. But at least for some interval of time that you can control and which is independent of n, you have control. So you can show that if you start with this less than 1 at a certain time tau, which is bounded below, it will be less than any constant you want. So we pick it 2 to the sigma. And then it's just about iterating in time. So we start from this quantity m. At time 0, it's equal to 1. It grows. And then here it's less than 2 to the sigma. Okay? So when we're here, we say, okay, but this quantity has many, many scales. Let me remove the biggest one. And if I remove the biggest one, because of the way that it's defined, I must decrease my thing by at least a factor of 2 to the sigma. So I remove one scale, the largest one, and I go back here on the removed quantity. And then I run the proof again. I say that after time 2 tau, I've derived here, I remove one scale, the largest scale, and then iterate. So it makes that on each given interval of time, I've done that a finite number of times, I've removed a finite number of scales, but I still get a quantity that's bounded. And then we can finish because of the remark that was here, I don't know, somewhere. Yes, that if a quantity like this is bounded, it implies convergence. So basically what we do is we play with this maximal n here. We just shave off one at every interval of time in order to finish. Okay, so now I can give you some results. First of all, we show that if indeed you take a regular enough initial distribution, you will have a unique, of course, regular solution on which you need many derivatives here. So this is the metric that we're using. So you want this to be controlled on some given interval of time. And this is the result for the sub-Coulomb case. So we assume that we have such a nice solution, we control these things. We need assumptions on the initial data. So the initial data assumptions are that basically at micro-scale behavior is very well tamed. So there's no, not too many particles that are too close initially. So you can control these sort of micro-scale interactions very well. So, and you need your initial quantities to be well controlled. So this is the M norm at scale eta. This is the weak norm that I described before, the W11 star. And you ask them to be less than C eta naught. So I remind you, eta naught is this. It's n minus 1 over t. So this is really the best. This is the best you can hope for. Okay, so if you have all these sort of good initial data assumptions, plus the assumptions on k that I spare you, then you get the control at later times. For every eta, you can go down almost to eta 0, so almost to the microscale. You control in terms of eta 0 over eta. Okay, so in the logarithmic case in 2D, there is a little correction to the power, but this is very minor because you see exponential square root log, it's not even a power. And you get the control of the weak norm, and the important point is that these estimates are essentially sharp because you cannot get better than eta naught. This is the microscale. And eta square is the price of mollification in this weak metric. Okay, so then thanks to these controls, but which are very quantitative, you deduce what you wanted, which is the weak convergence. And there is a corresponding theorem in the Coulomb case. So now S can go up to d minus 2, again with assumptions on k. And the only difference is the initial data assumptions are a little bit different. Here you assume separation of the initial points by a constant times the microscale. You again assume you have very good control of your initial metrics. And then the other difference is that you don't know if you can go to the maximal time that you control your solution. Okay, so the result is you may have to stop at a shorter time. Right, so your solution exists up to type t, and you can go up to some time t star, which is independent of n, positive, but so you don't control.
Time t, you are meaning for the limiting equation, right?
For the limiting equation, right? So you assume that over an interval 0t, you have a solution to the limiting equation for which you control many norms. Right. Okay? And here, you have convergence for some interval like this. And the reason why you can't go beyond is that we can construct counterexamples for which you have a collision at some time that's smaller. Because you see now you don't have repulsion in this setup. So the particles can actually attract and collide. Okay. So we build a...
But if you make an assumption that cannot happen, then...
Yeah, I mean, yes. So you can possibly put assumptions. In the other setup that I described before, this does not happen. The Coulomb case, we have existence for all time, for which we have the solution, but we take advantage of the repulsive nature of the interaction, the fact you have an energy. But if you don't want to assume you have an energy, you can be doing Coulomb inverse gradient flow, right? So inverse gradient flow. Okay, so you can make a counterexample like this. You put particles in dimension 1, very well spaced initially, except you make 2 of them be a little bit closer. So they are still well separated. And you see how long it's going to take for those two to actually collide. So it is going to be bounded below time, but they will collide. So that's why you cannot expect to go beyond a certain T star. And what we prove is that there exists, in the course of this, we also prove there exists a T star until which the ODE system continues to have solutions. Right? So the ODE system is already not clear that it's well posed. So up to T star, you do have a solution, and you have convergence with, again, these same rates that are essentially sharp. But you have to possibly stop due to the lack of existence of solution. All right, so this is just what I was saying. This is sharp because for attractive case, you could get collisions. And you can also make this method work in a super Coulomb case, but this time, the time for collision will not be bounded below by a constant. It will be very short. It will depend on n, and so you will have only for a very short time a result. Voilà. So I think it's a good time to stop.
Thank you very much.
Wait.
So are there questions?
Yeah, lots of them.
I hope the count is globally correct.
It's a midfield approximation.
Yes.
Can you add a diffusion in the proof, and if yes, how far are you from the supercritical case in collapsible?
So in the second method, we cannot yet add a diffusion. I think we will have to modify the method quite significantly. So this is something we're thinking about, but it will be a different norm. In the first method, that has been done. You can add diffusion. It makes the modulated free energy. So you combine the modulated energy with the relative entropy, and it works very beautifully. And what was your other question?
With the second method, how far are you from treating the supercritical Keller-Segal propagation of clouds?
What is supercritical Keller-Segal?
When there is a direct mass, which is...
So first you have to add the diffusion to discuss it. But you can do in some sense, we're discussing the one with collisions without the diffusion. So it's already the same spirit.
So is it true that you can, so the dialectic scaling you use is only for Coulomb, right? But for sub-Coulomb, can you remove that? Because sub-Coulomb...
No, we need it for all, we need for both.
But for sub-Coulomb, you have some extra room.
It's true, you have some extra room, so you can close the proof a little faster in some sense, but you still need to go down to all scales. Yeah.
Are there other questions, remarks? If not, let's thank Sylvia again.